All right, guys. I'll get started with the lecture today. We're going to be dealing with more general regions of integration in the xy plane. So far, what we've been looking at with double integrals. The first lecture on double integrals. Remember, I defined the double integral, and I talked about it in the context of volume below a surface and above a region in the xy plane. And the only types of regions we were considering were rectangular regions. The next thing we saw was that, it was great news. Whenever we want to evaluate a double integral, we don't have to take limits of these double Riemann sums every time. Instead, we can use this result known as Fubini's theorem, which turns the double integral into an iterated integral in terms of the two variables, x and y. And the iterated integrals are, in principle, easy to evaluate. All right, we just evaluate them much like we do with definite integrals of a function of a single variable. But there's still this, I guess, outstanding problem is up till now, we've only ever considered rectangular regions in the xy plane. So the question still remains, how do we deal with more general regions? And that's what this lecture is all about. Now, on page 60, we have a way of making a formal connection between what we've seen so far, where the regions of integration have just been rectangles. So this discussion just on page 60 here, you might just like to make a note that it's it is a formal connection with what we covered in lecture 7. All right, so let's just have a look at that. Let's just have a look at that and see what the connection is. So let's say we're interested in calculating this double integral of a function little f over some more general region in the xy plane. So for example, I could draw a diagram here, just a rough diagram in the xy plane. So we might have a region D that looks something like this. Okay, so that's the integral on the left-hand side. All right, the left-hand side of this equation up the top of the screen there. All right, however, what we can do is, well, so far we've only seen double integrals over rectangles, but what we can do is define or introduce a new function that I've called capital F here that takes on the same values as the function we're actually interested in, right, this function little f, provided the input is in this region D. Okay, so we define this function capital F to take on the same values as little f inside the region D, and 0 in some other rectangle that completely encloses the region D. So I guess I could draw in the rectangle here. Now the rectangle doesn't really have to touch the region D. They don't have to have common boundaries. That's not important, right? But what is important is that this rectangle that I've just drawn in, so that's what I've just called R, this rectangle in the xy plane. It completely encloses the region D. And then it turns out that defining this new function capital F, right, that takes on the same values as little f for points inside D and takes on the value 0 for all of these points out here that are in the rectangle but are not in the region D, that function capital F is still integrable. Remember how I define an integrable function? That's just a function such that the limit of those double Riemann sums converges. All right? So it's possible to show that the limit that defines this double integral on the right-hand side of this equation does exist. So we call that function capital F integrable in such a case. All right, then this is the connection that we make with the double integral on the left-hand side that we're actually interested in, and this double integral over a rectangle of this new function. All right, even though it's discontinuous, potentially on the boundary of the region D, it's still integrable. All right, so that's how we make this connection between what we've seen so far and these more general regions. However, that doesn't help at all with how we evaluate them. Now, what was it? Fubini's theorem. That was the result that allows us to evaluate a double integral as an iterated integral. So what we can do is generalize Fubini's theorem now to take into account these more general regions. Now, the strategy that we're going to use is to introduce two basic types of regions, right? Called type 1 and type 2 regions, right? Not very exciting names, but nevertheless, these two types of fundamental regions in the xy plane that will form the building blocks of much more complicated regions. So that's what I'm going to talk about now. I'm just going to talk about these so-called type 1 and type 2 regions, which will form the building blocks for dealing with much more general types of regions. Okay, and that will come about because we'll use the properties of the double integral. All right, so for instance, a complicated region like this, we could divide it up into smaller regions, which are either type 1 or type 2, and then I'll show you how to deal with such regions now. Okay, so we'll start with a type 1 region. What do we mean by a type 1 region? Well, these are the regions with graphs in the xy plane, or that look something like this in the xy plane. The key feature being is that we can always place the region between two constant values of x. So that's between these two vertical lines with the dashed lines here, with equations x equals a and x equals b, and place it between these two graphs of the continuous functions g1 of x and g2 of x. Right? So the key thing here is that we can represent the region using this set notation that I'm so fond of. We can represent a type 1 region always in this way. All right? Where we give... Well, actually, let's just revisit what this notation means, this set notation. We read this as D is the set of all points with coordinates x and y, such that the x-coordinate lies between the numbers a and b, and then given any value of x between a and b, the value of y is then bounded between g1 of x and g2 of x. So that's a little bit of a generalization of the type of notation we've been using, whereas now, well, the only real difference is now one of the variables has bounds which are functions of the other variable. All right, so that's the only difference. So remember, if all four bounds were constants, we'd be dealing with a rectangle. All right. So now what this is saying is you give me a value of x between a and b, so say this point here, and then if I draw a vertical line along that point, then I can see that the corresponding y value must be between, or must lie above this point, which is on the curve y equals g1 of x, and below this point, which is on the curve y equals g2 of x. In fact, what we're going to do now is, in terms of generalizing Fubini's theorem, remember how we made this identification with the double integral and Fubini's theorem? It wasn't exactly a rigorous proof I went through in the lecture. It was more just a visual justification by considering the volume below a surface. Okay, and the way we did it to arrive at the result of Fubini's theorem was to consider the volumes of slabs either, well, that were parallel to either the YZ plane or the XZ plane, right? There were these two different ways of doing it. Okay, so what we're going to consider now, actually let me just build on this, this diagram I've drawn here, is we'll use Fubini's theorem for type 1 regions, and what we'll do is divide the x interval from A to B. We'll divide that up into subintervals. So say here's one subinterval, and then what we'll do is approximate the volume below that surface, that is the surface with equation z equals f of x and y. So just down below this diagram. So we're interested in applying Fubini's theorem to this double integral over such a region. Okay, we'll split the x interval from A to B up into subintervals. So here's one of those subintervals. We choose a representative point. So inside that interval, I'll call that representative point x star. The width of the interval is delta x. Okay, and then we'll evaluate the function at this value x star so that on the surface itself we have a curve with equation z equals f of x star and y. So it's just a function of y only. All right, and that's going to define the top of our slab. So this is pretty much what I was describing in the last lecture. All right, so what we're going to do now is place such a slab on top of this rectangle that I've drawn that approximately sits inside the region. So just, I should always, perhaps I should have tried to draw such a slab or produce a diagram of such a slab so I didn't have to draw it under pressure in the lecture. So what we're doing, so let's say the slab just looks something like this. I'll shade in one side of the slab. So the width here is delta x. Okay, the top of that slab is just, I guess, contains the curve z equals f of x star and y, x star being the representative point. And so what we're going to do is pick up this slab, and let me see if I can actually grab that. So I want to pick up this slab and place it on top of that rectangle. And that's going to be an approximation for the volume above this rectangle, or at least above this part of the region D and below the surface. It's just an approximation at this stage. Okay, so what's the volume of that slab? Well, we talked about this last time. Remember, it's just going to be the dimensions, the cross-sectional area times the depth, which in this case, or width if you like, which is just delta x. So what about the cross-sectional area? In this case, the cross-sectional area will just work out to be the integral of the function f of x star and y. So this is just a function of y only now, right? We're taking our function f of x and y, plugging in whatever that number is, x star, and we just let y roam over values from, well, what's the lower bound going to be? Whatever that corresponds to, that will just be g1 of x star. So that's going to be the lower bound, g1 of x star, and the upper bound will be g2 of x star up here. So that's going to be the upper bound for the integral that gives us the cross-sectional area. All right, so therefore the volume of that slab is just going to be that formula for the cross-sectional area times delta x. Okay, then we just repeat the process for all these different slabs in the region. But notice one thing, this is where it differs from the rectangular regions, is as we move along the interval to another, say to another sub-interval, so say over here, you can see the dimensions of the rectangle, which forms the base of the slab, will be different. While the width will be delta x, the height of that rectangle will change. And it will change depending on the value of these functions, g1 and g2. Okay, so when we have another slab of this that looks something like this, and we place it on top of this rectangle, the formula for the cross-sectional area will be still be given by an integral of this form, but now the bounds will be different. They will depend on these functions G1 and G2. Okay, so that just gives us an approximation, but then we sum up overall the slabs, okay, and this gives us an approximation to the volume below the entire surface. Now what we can do is take the limit as delta x goes to 0, or equivalently, as we take more and more slabs, okay, with smaller and smaller width delta x, we get a better and better approximation. Finally, in the limit, we end up with an iterated integral. All right, so for these type 1 regions, we can represent the regions. Let me just scroll back up to that expression. We represent the regions in this way, right, where the x variable has constant bounds, the y variable is bounded by these two functions of x, and then what we can do is apply Fubini's theorem using this argument I've just been through, where we can turn the double integral into an iterated integral. The only difference now, remember with an iterated integral we work from the inside out, so this means we evaluate the integral with respect to y first. Okay, so when we evaluate this, we're still treating it just like a definite integral of a function of a single variable. So in other words, we work out the antiderivative of this function partially with respect to y, treating x as a constant. Okay, so then, that other screen's really not in focus, is it? Yeah. So once we work out that antiderivative, we substitute in these bounds, which are functions of x now. Okay, so that's the difference between this case and the rectangular case, is for the type 1 regions, the bounds of the inner integral are functions of x. So when we substitute in those bounds, we'll still be left with just a function of x only, and then we can evaluate that integral with respect to x to obtain the number that that represents that double integral. Okay, so that's the type 1 regions. Actually, I've brought along just a little demonstration. Let me just put this up on the screen. So actually, I forgot to bring my my printout with this example written on, but it's actually I just wrote it up. Well, I just wrote it up quickly before. Oh, come on! I just wrote it up quickly before I started the lecture. So now I think I've got the surface right. But what I'll do when I scan in my notes, I'll make sure I include the printed version of this. But I'm pretty sure I've got it right. Anyway, really the details of this surface is not so important. But let's just have a look at the example. We'll consider the volume above the region in the xy plane bounded by these three curves. So one is x equals 0, which is just the y-axis, right? You can see in the diagram I've got the axes labelled, so the y-axis. We've also got the parabola, y equals x squared, so you can see the blue curve hopefully is clear to you that which one represents the parabola and which one represents the line y equals 1. So you can see the region there. I can't see any pointer, but hopefully it's clear to you that you can see that region in the xy plane bounded by those three curves. All right, so now we're interested in the volume above that region and below the surface with equation z equals 4 minus x squared minus y squared. So I've just included the part of that surface that sits immediately above that region in the xy plane. So what we're interested in doing for this example is working out, or at least approximating, the volume of that solid that I've got outlined there. So now, just with the slabs, using slabs, I just want to show you what the approximation would look like. Now, this isn't using any numbers, so it's not really a quantitative approximation. I just want to give you an idea of what the slabs look like. Okay, so now if we partition that x interval up into 4 subintervals, we end up with 1, 2, 3, 4 slabs. Okay, and we calculate the volume of those slabs by just working out the width along the x direction, so the delta x, whatever that is, In fact, I think in this case, because it's from x equals 0 to 1, the width will just be 1/4. And then we also, I think in this example, the representative point in each subinterval I chose was just the midpoint, right? So I evaluated the function, which is just 4 minus x squared minus y squared at that midpoint, whatever the midpoint is in each subinterval, and then define the top of the slab to have equation z minus some constant minus y, z equals some constant minus y squared. All right, so those are the 4 slabs. Now, one thing I really I want to point out is see how the length along in the y direction of the base of those slabs changes. Right, that's the key difference between these more general regions and the rectangles. Okay, so anyway, now if we take 8 subintervals, we end up with 8 slabs. Right, so the approximation would look something like this, and the idea is we'd have a better approximation to the volume below the surface. Now with 16 slabs, corresponding to 16 subintervals between 0 and 1, and finally 32. So remember, the volume of that slab there is just going to be the width times the cross-sectional area, and as we're getting smaller and smaller, we're ending up with a better and better approximation to that volume. Okay, so finally in the limit, as the width of those slabs go to 0, we end up with the iterated integral from Fubini's theorem. All right, so I'm not going to calculate anything with this example. I just wanted to show you that little demonstration just to, I guess, really highlight the difference between these more general regions in the xy plane and the rectangles. In particular, seeing how the length of the base of those slabs is changing depending on the subinterval. Okay. So, all right, that's just, well, I guess enough about Fubini's theorem. On page 61, I've just given a couple of examples of some graphs of type 1 regions. So the key feature is with a type 1 region, we can place it between 2 vertical lines, x equals A, x equals B, and then say, just giving that information is enough to say, well, the region we're interested lies in this infinitely long strip, right, parallel to the y-axis, and then we cut that strip in 2 places. One is the curve y equals g1 of x, and the other is the curve y equals g2 of x. All right, what about an example? So now we're being asked to find the double integral of 4x plus 10y over some region. And it describes the region, right? So we don't immediately have a description of the region in this form, using this set notation that I'm rather fond of. But hopefully, after going through this this example, you'll see, or at least I'll demonstrate, why it's important to, as a first step, obtain such an expression for the region. Okay, so this is what we're going to work with. We're going to try and apply Fubini's theorem. So let's first just get an idea of what the region looks like in the xy plane. So I'll draw up a rough diagram. So we're given that it's bounded by the parabola y equals x squared. So I'll draw that in. Y equals x squared. And we're also given that the region is bounded by the line y equals x plus 2, which might look something like this. Right, not a particularly accurate diagram, but it doesn't matter. I just want to get some sort of an idea for what the region looks like. Okay, so here's the region D that lies between the parabola and that straight line that I've just drawn. So now, one thing I can do at this stage is identify it as a type 1 region. Namely, I can draw in 2 vertical lines, so I can identify these points where the 2 bounding curves intersect. 2 vertical lines which completely contains the region. So the leftmost point of the region will lie on this vertical line, and the rightmost point up in this corner sits on this vertical line. So now I want to work out what those x values are. So in this case, it's important to work out the points of intersection of those boundary curves. Okay, and so if I just set the equations for the two curves, so x squared equal to x plus 2, we end up with a quadratic in x that we can solve, and the two values of x are just 2 and negative 1 that satisfy that equation. All right, so here's x equals 2, and here's x equals negative 1. Right, so those are the two x bounds. So what I'm seeking to do here is provide a description of the region of this form. So all we've got at the moment is that the region D is the set of all points with coordinates x and y, such that the x coordinate lies between x equals negative 1 and x equals 2. Okay, now what's left is to give bounds for the y variable. All right, so just giving that information, all that says is that the region we're interested in lies somewhere between x equals negative 1 and x equals 2. Okay, these two vertical lines. But now I want to narrow down the region by providing the additional information of the bounds of y. And so now what we can do is start to look at values of x between negative 1 and 2. So if I were to split up this x interval into subintervals, I could start drawing in these small rectangles, okay, which will form the base of the slabs in the approximation of corresponding to Fubini's theorem. But so in each case, what you can see is in the y direction, the lower bound for each rectangle always sits on the parabola, which has equation y equals x squared. So that means any point inside the region will have a y coordinate that is greater than x squared, right, given some value of x between negative 1 and 2. So the lower bound is going to be x squared. Right. Similarly, you can see the tops of these rectangles lie on the line y equals x plus 2. So the upper bound will be x plus 2. Okay, and now we've got all the information we need to apply Fubini's theorem. So we can write down that the double integral of 4x plus 10y dA is this iterated integral now, where we've identified it as a type 1 region. Now, corresponding to the type 1 regions, which always give constant bounds to x, and the bounds for y are, in general, functions of x, that means the first variable in the iterated integral, the inner integral, must be an integral with respect to y, because the bounds are functions of x. So that's lower bound is x squared, and upper bound is x plus 2, and then we're integrating finally with respect to x between negative 1 and 2. All right, I'll just go over the page and put this on the other screen. Okay, so now it's just a matter of evaluating that iterated integral, okay, which is relatively easy to do. So we integrate first with respect to y. Remember, we work from the inside out. Integrating that function, 4x plus 10y, is just going to give us 4xy plus 5y squared. And then that's evaluated from y equals x squared up to y equals x plus 2. Okay, and we're treating this like a definite integral. Okay, where we're treating x as a constant at this stage. All right, so now I substitute in the upper bound. So that's 4x times x plus 2 plus 5x plus 2 all squared, and then minus the expression obtained when we substitute in the lower bound. So in this case, y equals x squared, we'll get 4x cubed plus 5x to the 4th. All right, so now this is just a polynomial in x that we're integrating. So it's my belief that there's no value in going through the minutiae of that calculation. But you might as well go through it in your own time and check that the answer is 81. I mean, there's no value going through it in this Math 2000 lecture. All right, so they're the type 1 regions. Now, What about the type 2 region? So these are the other types of regions which form the building blocks for more general regions. So it's just pretty much the same as the type 1 regions, except it's all rotated 90 degrees. All right, so in this case, the type 2 regions are just the regions that can be expressed in this way. So at the bottom of the screen here, there's this expression for the region as the set of all points with coordinates x and y, such that now it's the y variable that gets constant bounds, and the x variable has bounds which are given by functions of y. All right, so this is just a general sort of picture of what the regions look like. So now what we could do is think of it in terms of Fubini's theorem. Now what we can do is partition the y-axis up into subintervals, and then on each subinterval of width delta y, we choose a representative point, y star, evaluate the function we're integrating at y star to define the top of the slab, and then we have these rectangles running parallel to the x-axis that define the base of those slabs. So you can see as we move along up the y-axis to the different subintervals, right, the lengths of these rectangles will change depending on what the functions h1 and h2 are doing. Now, I'll just point out that since the positive x direction is to the right, that means it's always this curve that sits on to the right of the type 2 region, which is the upper bound for the x variable, and the one that sits to the left, which is the lower bound for x. Right? Pretty much everything else is the same as the type 1 regions. It's just all rotated 90 degrees. So now we're taking our slabs, putting them on these rectangles, approximating the volume below the surface, and so on. So the outcome of all that is that we end up with another type of iterated integral, but in the reverse order to the type 1 regions. Okay, so whenever we've got a type 2 region, we can express that region in this way. Okay, and then that allows us to apply Fubini's theorem, okay, where the inner integral in the iterated integral is representative of the cross-sectional area of those slabs that run along parallel to the xz plane. All right. So now we've got the second type of region that we can evaluate using Fubini's theorem. Okay. So I won't go into the careful discussion of of slabs and all that again. I feel like it's enough that I've been through that for the type 1 regions. It's more or less the same argument. Okay, just with the variables switched around. Okay, now let's look at this example. We're being asked to evaluate this double integral of the function xy, where D is the region bounded by these two curves in the xy plane. One is the line y equals x minus 1, and the other is this parabola. So again, let's just start the example by looking at a diagram of the region. And what I'd really like to do, just as a first step, is work out an expression for the region of this form, which then will allow me to apply Fubini's theorem. Okay, so what is just a rough diagram of the region, just to get an idea of what it looks like. The parabola y squared equals 2x plus 6 will look something like this. So I'll just label that y squared equals 2x plus 6. And then we've got the line y equals x minus 1, which might look something like that. So here's y equals x minus 1. So that's the region D that we're interested in there. Okay, so now the thing is I can identify this as a type 2 region because I can see that I can place this region between two constant values of y and where the corresponding x values will be bounded by only these two smooth curves. Right? So for the y values, I can see that the upper and lower bound will correspond to those points of intersection of the two curves. So again, it comes down to working out these points of intersection of the two boundary curves. All right, so in this case, I could just take the equation for that parabola, y squared equals 2x plus 6, but substitute in the other equation for x. So just rearrange that so it's in the form x equals y plus 1. Okay, and we end up with a quadratic in y. That should give us the two points. So that's just y squared minus 2y minus 8 is 0. So y is going to be 4 or negative 2 in this case. All right, so here's y equals negative 2, and here's y equals 4, the lower and upper bounds respectively. All right, so now we can get started with writing down this representation. Leave a bit of room. Writing down this representation for the region using this set notation, so D being the set of all points x and y, such that now we know the y variable has constant bounds, which in this case are negative 2 and 4. And so what are the corresponding bounds for x? Right, that's all that's left to work out. Well, if I choose a value of y in this range, this is where I can start drawing those rectangles. Right, so given any value of y, a corresponding rectangle, which I guess would be the base of those slabs in the Fubini, in the slab approximation to the volume. I can always see, remember the positive x direction is to the right, that the lower bound for x, or the leftmost points of these rectangles, always sits on that parabola, y squared equals 2x plus 6. But I want to represent that in the form x equals some function of y. So I can rearrange this as x equals, what will it be, y squared minus 6, and then divide by 2. So that's going to be the lower bound then, a half y squared minus 6. Okay, all points on the parabola. And also the upper bound then, I can just rearrange the equation of the straight line to be x equals y plus 1. And so that will be the upper bound for the region. Okay, just going over the page now, we'll get to the point where we apply Fubini's theorem. And so now that we've got this nice expression for the region, I can apply Fubini's theorem and just read off the bounds from that expression. Okay, so that implies the double integral over the region D of the function xy can now be turned into an iterated integral by Fubini's theorem, because this is a type 2 region. So we're integrating the function xy. Now, because the x variable has bounds which are functions of y, we must integrate with respect to x first. Okay, that's the corresponding order of integration, that corresponds to the type 2 regions. So we first integrate with respect to x, beg your pardon, where the lower bound, just reading off that, I had a half y squared minus 6, and the upper bound was y plus 1. Right? That's the inner integral, and that's the one that corresponds to the cross-sectional area of those slabs. Right, and finally we integrate with respect to y from negative 2 to 4. All right, so again, it's just an iterated integral. We work from the inside out. Find the antiderivatives of the function. So first, the antiderivative with respect to x, okay, treating y as a constant. That's just going to become a half x squared y evaluated from x equals a half y squared minus 6 up to x equals y plus 1. All right, and then we substitute in those bounds. The upper bound first, so that's a half y plus 1 squared times y, minus the value obtained, or the expression obtained when we substitute in the lower bound. So that's just a half. So lower bound squared times y. So what's that lower bound? It's just a half y squared minus 6. All right, we could expand that. It's just going to be a polynomial in y. So again, I don't think there's any value in going through the details of that calculation, the rest of that calculation in this lecture. But just check that the answer is 36. Let me just go back to something. All right? Consider this function we're integrating. F of x and y is, in this case, is x times y. Now just consider this. On so the region D lies in all four quadrants, right? Quadrants being positive x and y, negative x and y, and variations. Okay, so now let's have a look. When x and y are both positive, so in this first quadrant, we can see the function takes on positive values. When it lies in the quadrant where x and y are both negative, f is also positive. But in these other two quadrants, say where y is positive and x is negative, right? Positive times a negative number, that's negative. So the function outputs a negative value, and same for this quadrant down here. So up till now, when I talked about the double integral and I talked about volume below a surface, remember at the very first lecture on double integrals, I said let's keep it simple, so we'll keep the region in the xy plane is just a rectangle, and we'll insist that the function only takes on positive values, meaning it really is the volume below that surface and above the xy plane. But now in this case, the surface z equals xy actually dips below the xy plane, right? It drops below the xy plane on those two quadrants I've highlighted there, with positive y, negative x, and positive x, negative y. So this number 36, which is the result of the double integral, what does that represent? Right? How can we interpret that result? I mean, what is the volume below the surface in this case? Because it's a little bit more complicated than that. And that's where I introduced this concept that I call net volume. And we'll say net volume above the xy plane and below that surface, z equals f of x and y. But what I mean by net volume is literally the volume of the solid, or part of the solid that sits above the xy plane, minus the volume below the xy plane. Okay, let me just draw a parallel between something you're familiar with. Consider the graph of sine x. So just a really rough diagram here, but consider the graph from 0 to 2 pi. And if we integrate sine x with respect to x from 0 to 2 pi, you know we get 0. Okay, but how do we have this? How do we interpret that in terms of area below the curve? Well, it's just going to be, I guess you could call it net area, right? It's just the area of this part that sits above the x-axis minus the area that sits below. Okay, so I guess we could say that 0 is just the net area, right? So now we understand how to interpret the net area below a curve of a function of a single variable. The concept is much the same for functions of two variables, right? Where it's not area below a curve, it's volume below a surface, okay? And where that surface drops below the xy plane, right, you're subtracting off that volume. Okay, so that's what this result would represent. That's what the number 36. That's what the number 36 would represent, the net volume. Okay. So just something else that's worth considering. Okay, so now that we've got these building blocks of more general regions, so the type 1 and type 2 regions, what do I mean by that? What do I mean by building blocks? Well, consider a region such as this one, on page 66. So it turns out this region is neither type 1 nor type 2, but I can represent it as a union of type 1 and type 2 regions. And there are actually heaps of ways of doing it. There are lots of ways of doing it. So if we call this region D, we could use the properties of the double integral on the workbook. I think it's page 51, right? Especially property number 3, where we'll use the strategy that we'll take this really complicated region and just try and divide it up into smaller regions, which are either type 1 or type 2, right? And we can do it with as many regions as we like, as long as we get those smaller regions to be either type 1 or type 2, because it's on those type 1 or type 2 regions that we can apply Fubini's theorem, right? We've just worked out how to do that for both those types of regions, okay? So, and then use these properties of the double integral. So there's one way of dividing this region up. I think the simplest way of doing it is to draw a line across here at y equals 1, and then we have this region which sits above y equals 1, so I'll call that the region D1. And I can identify that as a type 1 region, because the region sits between x equals -1 and x equals 1, and between just two continuous functions of x, namely y equals 1 and y equals x squared plus 1 being the parabola at the top there. Okay, but drawing the line across there, what's below that line? Well, I can identify what remains as a type 2 region, because the region sits entirely between y equals -1 and y equals 1, but most importantly between only two continuous functions of y, namely to the left x equals -1 and to the right x equals y squared. So I'll call that region D2. And then we have that the entire region D is just the union of those two regions, or the disjoint union. Okay, so what we can do now, if we were integrating or interested in integrating some function of x and y over this region, we'd want to apply Fubini's theorem, but we realize this region D is neither type 1 nor type 2, so it's not as simple as just applying Fubini's theorem to the region D, but we can use the fact that it's the union of a type 1 region D1 and a type 2 region D2, and this is one of the key properties of the double integral, is in that case, where it's a disjoint union, we can write the double integral over D as the sum of the two double integrals over D1 and D2. Right? Now, we can apply Fubini's theorem to those two separate integrals. All right, so for example, for D1, I can see, well, actually what I want for D1 as a type 1 region is constant bounds for x. Okay, so let me just scroll back up, or I wonder if I could just get it all on one screen and zoom out and you guys still be able to see. Is that all right? Can you still read that okay? So look, you can see the constant bounds for D1. The x variable is between -1 and 1. And then the y variable, given those constant bounds for x, will be between y equals 1 as the lower bound and y equals x squared plus 1 as the upper bound. So that's for D1, which is the type 1 region. Now for D2, which is the type 2 region, I want to give constant bounds for y. So I can see for D2, the lower bound will be y equals -1 and y equals 1. So just giving that information is just saying the region D2 lies somewhere between those two lines, y equals -1 and y equals 1, right? The infinitely long strip. But to nail down the region, I need to also give the bounds for x as functions of y. And to the left of D2, I can see it's bounded by the line x equals -1, so that's the lower bound. And the upper bound must then be x equals y squared. All right, so now I can apply Fubini's theorem to both of those integrals and end up with the following expression. So the integral for D1, we first integrate with respect to y from 1 to x squared plus 1, and then with respect to x from -1 to 1. So that's the iterated integral corresponding to this first integral over D1. And then over D2, that'll just become the iterated integral where we first integrate with respect to x from -1 to y squared, and then with respect to y from -1 to 1. Okay, and that's how we do it. So now, hopefully, after seeing this this example, I mean, it's a reasonably straightforward example, right? We just need two subregions that are either type 1 or type 2. But this is what I mean by the type 1 and 2 regions being the building blocks for more complicated regions. You can imagine now if we had some really complicated region where the best we could do is split it up into 7 different regions, we'll just treat each one of those regions separately. Is it type 1 or type 2? And if whichever one it is, apply Fubini's theorem to that and use these properties of the double integral. So now we can deal with much more complicated regions of integration for double integrals. Okay, guys, I'll stop there. Thanks.